So in 7.1, we talked about momentum impulse theory and what momentum was and what impulse was. Can somebody give me an explanation in their own words of something to do with how you would state momentum and its value and how that translates into impulse and what impulse is? Could you put that in your own words? Start with momentum, that's fine if you want to. Momentum, we should kind of all know what momentum is by now. What do you think momentum is, Joe?
Well, momentum is like the combination of a person's like mass and velocity, and it's basically like the overall like not speed, but actually
speed and mass.
Yeah, kind of speed and mass together.
How do we operate on them? Do we add them together, or what do we do?
What you do is you multiply.
Yeah. So the product, very good. The product of the mass and speed, and Joe's right. It's both. So you can have a lot of momentum. We talked about this many times now by either having a lot of mass or a lot of velocity. But if you have a really low amount of one of those two, it might counteract the other, right? So it's really about a balance. We've seen this before many times now. So we did examples with a bullet and a bowling ball, and the necessary velocity for a bullet to have the same momentum of a bowling ball. We talked about how it was far beyond the speed that a bullet could even travel at. We then talked about, I think, in either this section or this section, that some of the answers broke the speed of sound, actually. So we have to consider the fact that both of these parameters affect it. This is similar to what other entity that we've recently studied? Momentum is similar. It's not the same thing because the formulas are different. But it's similar to kinetic energy. Why? Why? Besides Rick, because he knew already. Why is it similar to kinetic energy?
Because it's like an energy out when you move.
Yeah.
If you're not moving it out.
Momentum and kinetic energy both depend on motion. Very good. Okay, and pretty much all other energies also depend on mass. Mass is dependent for a lot of energies. Potential energy involves mass, right? We're going to see that if we even just consider things beyond mechanics, that mass plays a role in a lot of different aspects. But specifically, the velocity is the key here that is in both expressions. Good. Impulse, let's get into that now. What was the deal with impulse?
It's the change in momentum is the impulse.
Yeah, very good. That's a good way of putting it. The change in momentum. So let's write that one down to start. The change in momentum is equal to the impulse. Bless you. So the impulse is the product of what variables then? I'm saying it like this.
Force times time.
Good. Force and time. The product of force and time is impulse. If a problem says, what is the impulse felt by an object, and you're given a force and a time, just multiply them, and that's the impulse felt. The key is that the impulse you feel equals, as Isabel said, the change in momentum. Change in momentum. Not the momentum of an object, but the change in that object's momentum. So by change, we really mean final minus initial. Bless you. The formula that you're given on your formula sheet is the first one with the delta symbol. You need to make sure that you understand how to process through this. Since momentum is defined even earlier as mv, we can replace these with mv. But what should I do? I can't just call them both mv, right? Well?
Mass velocity final minus mass velocity initial.
Good. So in reality, that's the momentum impulse theory, but it depends on what the problem gives you. If a problem tells you the starting and ending momentum, you can just take the starting, subtract it from the ending, you get the change in momentum, and that's a number, and that equals ft, and you're going to solve for problem one of these. If the problem tells you the momentum changes by 10 kilogram meter per second, it's right here, 10. If the problem gives you an initial and final velocity, and maybe a mass, it goes here. Maybe you're finding the mass. Maybe this is friction, so it becomes mu mg, which we've seen many times now, and the mass is all canceled out. So depending upon the scenario, we need to be able to manipulate these sets of formulas, really, of which they really come from only two, which is why these are given on your formula sheet. Those are the real formulas that they all stem from here in section 7172. But from those two formulas, we can continue to get these two at the bottom here. Okay. So when you're practicing your problem sets and your homework, you want to step our way through from beginning of momentum impulse theory to the second line, to the third line, depending upon what the problem gives you. Again, given velocities, boom, go here. Given the actual momentum before and the momentum after, go here. Given the change in momentum, you go here. Okay, so it's one of those three lines that you're looking at. If you're actually given the impulse, replace, so the impulse is 10 kilogram meter per second. Replace Ft with 10. Replace this whole quantity with 10. If you're given impulse. But if you're given force and you're given time, make sure to plug them in the appropriate spots. Where did I give an example of this? I went on a big spiel about this. Talked about soft hands. How do we relate impulse and change in momentum to something that's physically around us? Yeah. Yeah, the concept of catching something and by cradling it, by increasing the time period. Very good. So if you just allow something to smack you in the hand and you change its momentum by a lot, and you change it like instantly when it hits you, it's going to take a lot of force to do that. But if instead of changing the momentum for like maybe a tenth of a second, instead you catch it and do this, it takes like a full second to do this, right? So you're increasing the amount of time, which decreases the amount of force. So let's jot down that force and time are indirectly related here, assuming the change in momentum is a constant. Again, assuming the change in momentum, the left-hand side, is a constant, force and time are indirectly related.
It's constant.
If delta P is constant, correct. If the left-hand side of that equation is constant, meaning the same scenario twice. A ball is hit, it slows down. A ball is hit again the same exact way, and it slows down differently. While the ball was hit the same way, meaning it has the same velocity, so the left-hand side isn't changing. It's going from some velocity to no velocity, right? Because VF is 0 if you're going to stop something. So really all that matters is the VI. And we recognize that F and T change indirectly. More time, less force. Less force. If you've ever seen, in horseback riding, if you ride a horse, as you're riding on a horse, every time you land, the impact from landing, you don't want to absorb it on your bottom. You don't want to absorb it on a part of your body. You would probably, I'm thinking about this because in your textbook they give an example of this. Every time you land, your legs would absorb that shock. That's what's happening here is instead of hitting, every time the horse lands, you're literally landing, you're probably using your muscles in your legs to increase the time period here. And it decreases the amount of force felt on your body. The book also does one on gymnasts. Same concept. If you demount from an uneven bar, or uneven bar, is that what they're called? When you see somebody dismount from there, they'll spin through the air and they land. And when they land, they always land, they go, and then they put their hands up, right? Don't they always tuck for a second there? Why are they tucking?
It absorbs the shock.
Yeah. If they land like this, I did it in class, right? I was like, if you do that, it can actually hurt your teeth. Try it sometime. Jump down from a very low height, not from a high height. Jump down from an inch or two, make a step, and land with your knees locked. It hurts. Actually lock your knees and try to land. On that, you'll feel the whole thing vibrate through your body because you're not absorbing the shock. You're getting a lot of force. That force is impacting your body and is resonating through. So you literally can feel it versus when you land and you literally absorb the shock in your knees. Momentum is a vector quantity. What does that mean? Vector. Talk about it right here. Matters here. Momentum is a vector quantity. Kinetic energy is not a vector quantity.
It matters if it's right or left.
Good. Direction matters for momentum. If I'm moving right, it's positive momentum. If I'm moving left, it's negative momentum. So direction matters. It's a vector quantity. Let's get into conservation next. So that's pretty much the first section. That's 7.1 and 7.2 that we covered in the beginning of this. Then we went into 7.3, which was conservation of momentum. Collision/explosion, I wrote on the side. Collision/explosion. So conservation of momentum, here it is. There's your formula. Okay, conservation of momentum. I'm actually really nice in this topic. I think on the formula sheet I actually give you those other equations. Okay, for elastic and inelastic collisions. I'm pretty sure I give you the equations after this. But this is the governing equation right here. This is all that matters. Just like MEI equals MEF, we came up with the equation from that every time with energy. This is our governing equation that says the momentum in the beginning of the problem after the collision equals the momentum. Sorry, the beginning of the problem equals the momentum after the collision itself. So this is before collision, this is after collision, or explosion, depending on what you're looking at. So for an example where you have three masses colliding, three, all of them moving, and then one of them stops afterward, what would that look like? Three masses all moving and colliding, and then two of them moving afterward and one of them stopping. What would I write down here? What would you go with here for a formula? We haven't done three masses, but I'm going to show you that again. We talked in class. Doesn't matter how many masses you do, keep accounting for their momentum before and after. So three are moving before, two are moving after. What would I write as an equation?
M1 initial, M1
Initial, got it.
plus M2 V2 initial plus M3 V3 initial equals M1 V1 final plus M2 V2 final plus 0.
Good. And the third one, good, is not moving afterwards, so plus 0 at the end. So this would be an example of three-body system where they all collide. They believe two of them are moving this way, and one is moving this way, and they hit, they go, boop, and the outer two move outward, and the middle one stays still. Whatever it is. But the concept I want you to see is that the governing equation is all that matters. Right? That's all that matters. Then, based on the scenario, you write your equation from it. Okay? If only one up, yeah.
What if there's two objects collide and they keep going,
Together?
and the energy loss, the definition, do we count that in the equation or not?
So for that example, we have them combining, you're saying, afterward, right? So the right-hand side is different. So I was going to go through, can I go to the next one? It's going to answer that, actually. So I was going to say one object, massive, or one object, attacking another object at rest, and they stick together afterward. What would that equation look like? Rick?
Like M1 plus M2 combined.
Okay, where? Rick, tell me the equation. Where would I combine them?
After the equal sign, so they're minus. Yeah, then we
And what about the left-hand side? What would I put? Go ahead, sorry, yeah. I erased it, but again.
M1 V1I.
Good. Again, the second object is standing still or sitting at rest. So that would be the example for two objects stuck together. Now, you asked about energy loss, though. Energy loss needs to be calculated via kinetic energies. So I have the mass, and I have the velocity to start. So I can find the kinetic energy using 1/2 m1 v1I squared to get the kinetic energy. Then after the collision, 1/2 m1 plus m2 vf squared. Because now they're acting as one body. So the kinetic energy after the collision involves a mass that's a lumped mass, a joined mass.
And then that wouldn't be true.
So this is just momentum here. This is not kinetic energy. There's going to be kinetic energy loss is what I'm saying. So when you subtract them.
Even if there's kinetic energy loss, there's no momentum loss?
Correct. Momentum is always conserved. So in 7.4, that's a great question, guys. In 7.4, when we talk about inelastic collisions, we say that energy is lost due to deformation and such. Momentum, though, is always contained, even when energy is lost. It's always conserved. Always conserved, even when energy is lost. So whether it's elastic or inelastic, momentum is always conserved. Always. Okay, so these equations up here are always true, Rodrigo, the ones you're seeing, for momentum. But then later, we're going to go ahead and we're going to find the kinetic energy initial and the kinetic energy final. So initial kinetic energy in this case, for this problem, hypothetically, let's say we're looking at this problem here. One object moving hits the other, and then afterward they're moving together. Okay, that's the scenario we're looking at. This one attacks, hits, they combine. We would have initial kinetic energy of 1/2 m1 v1I squared. And then afterwards, since they combine, the masses are a sum. And these will not be equal to each other. Okay, the KEI and KEF are not going to be equal when they join together because it takes energy to join together, so there can't be the same amount of energy that you started with as you ended. Okay, for that reason. So these will not be the same in this scenario when you're joined together. But in a scenario that's elastic, where they hit, bounce off, don't deform, there's no sound heard, pretty much impossible to do this, no sound heard, no heat loss, then you could say that kinetic energy before is equal to kinetic energy after. Again, I'm talking about a scenario like this one up here. This is where kinetic energy I will equal kinetic energy F. No energy is lost in this problem because they collide and bounce off. Nothing is sticking together. Let's assume that we're told that it's elastic. We're told it's elastic. Yeah? Okay. Problem set questions. Because some of you I know have started it, or homework questions. Let's take some of those. Problem set or homework. It's kind of the spiel I want to give you. The 7.3 and 7.4, we've noticed are the same thing, right? 7.4, you just kind of add on the whole idea about energy. 7.3 and 7.4, we're doing the same thing. Okay, it depends on what equation you're going to use. What questions do you have from homework or problem sets? Rick, go for it first.
For problem number 76 of the problem set,
Got a page by any chance?
yeah, page 260.
Okay.
When it was talking about the airbags, is it because like it's going to decrease the time, so in turn there's...
Oh, this is the impulse one, right?
Yeah.
It asks about why is there lower force on your body, airbags on the car versus no airbags. So airbags, the concept behind them is that normally when you hit the dashboard without airbags, how much time do you hit the dashboard in? Bam. Instantly, right? But when airbags are actually triggered, what they do is they cause your body to slow down in a longer time period, increasing T. So what does that have an effect on the problem, Rick? What do you think happens if you increase T? Less force. The airbags are slowing you down in a longer time period. Others? Homework, problem set questions. I want to open the floor to you guys because you have questions. Go ahead.
On the homework for
7-4,
7-4, number 58.
number 58. Do you have it in front of you by any chance, or you want to grab the text section? 7-4, number 58. All right. So number 58 says the following. This is page 256. 58 says, Brittany stands at rest on a skateboard. The combined mass of Brittany and the skateboard is 61 kilograms. Dave tosses a pumpkin to Brittany. The pumpkin's mass is 3.7 kilograms. When she catches it, she and the skateboard then begin to roll backward with a given speed of 0.16. What was the speed of the pumpkin thrown to her? What was the speed of the pumpkin thrown? What do you got? What do you got as an equation? I mean, not just an answer. Give me the governing. It's okay.
I should be 2I equals M1 plus M2 times V up over M2.
Okay, go back another step if you don't mind. Tell me the beginning governing so we can actually see. Yeah, that's right.
M2 times V2I equals M1 plus M2 times V up.
Very good. So what's happening here is this. Brittany and the skateboard are object M1. Pumpkin is object M2. Object M2 is tossed at the person. So Brittany and the skateboard we call just M1. So that's what they are. The pumpkin is M2, it's launched, so it's got initial velocity. She catches it, and after she catches it, it causes her and the pumpkin, after she catches it, to then move backward. But they're moving together because she caught the pumpkin. So that's why that's the afterword, okay? So this is V2I, and this is just VF at the end. So there's your governing, and your goal is to find the velocity of the pumpkin. So as Isabel mentioned, it's V2I that we're looking for. So just isolate V2I. If you call Brittany M1, or if you call Brittany the pumpkin M2 instead, if Brittany the skateboard M2, we just have the reverse. Again, the subscripts don't matter though, right? The subscripts aren't mattering as much if you call one, and the other two. Still the same answer. Understand? Look at the next question as well. Questions on this one? Yeah, Barnes, something else? Go for it.
88 in the concept.
88 on the problem set. That's got to be further in the pages. Where is it? All right, so page 261. Number 88 says, and this is a conceptual kind of question, right? Says, a system consists of two objects. If the total momentum of the system is conserved, does this mean that the momentum of each object must remain the same? And explain. Correct? Is the one? Anybody want to take a stab at that? What do you think, Joe?
I wrote the momentum of each object does not necessarily have to stay the same because they do not have to share the same velocity/mass, or if they stick together and there are more reasons.
Okay, good. And can you follow up with a little bit more, like another part? I agree. He's right so far.
Yeah, I was going to say the reason why they doesn't have to stay the same is because if there's no, what was it? Oh, I forgot what I was saying. You have to come back to it.
That's fine. You're on the right track. You got the first half correct.
Yeah.
You just have to conclude with something. I would conclude with, if one object loses momentum, fill in the rest. If one object loses momentum, the other gains it. So they don't have to remain the same at all. They can lose. I can lose momentum in a collision, and you can gain momentum, right? But the system as a whole, you and I, or two objects colliding, has the same momentum. It's just transferred. Okay? The system as a whole has the same momentum. So if two objects are about to collide, one with momentum 7 and the other with momentum -2, that's just 5, right? 7 to -2. So afterward, it's got to be 5. It could be this one goes back to 8, and this one goes back to -3. In the end, it's still 5, all right? So the momentum of the system is never changing. Each individual object's momentum can change. Momentum, in that case, single, can change. Got a good amount of time still. You got to be able to make conclusions and draw conclusions about things that we've talked about already. So we've talked about a lot of the lab demo, all fair game, especially the stuff we did in the demo more than even in the lab there. We had a concept where we had two carts of equal mass. Remember Rodrigo, the answer to them? When they're equal mass, as Rodrigo said, if one stops, the other automatically moves with the exact velocity change. If they're starting together and they're equal and they separate, they're going to move equally with equal velocities. But if one is bigger and the other is smaller and they separate, one moves really fast, the smaller one, and one moves really slow, the bigger one.
What's the difference between the problems from 7.1, 7.2, and 7.8,
7.1 and 2 is momentum impulse theory. Delta P equals Ft. 7.3 and 4 are both pretty much the same. It's the conservation of momentum. M1 V1I plus M2 V2I, that stuff. But 7.1 and 2 is very different. The math involved. It involves force and time and change in momentum. Yeah.
From homework 37, this is on version 47.
Yep. Let's take a look. Page 247. So number 37 says, an object resting on a frictionless surface is struck by a second object. So here's object 1, here's object 2, it's struck, so it's moving toward it. Is it possible, this is a great question, is it possible for both objects to be at rest after the collision? Is it possible for one of the objects to be at rest after the collision? Thoughts?
Which one was this?
This is homework 7-3. It's on the board. Number 37, page 247. What are your thoughts? Yeah, what are you thinking?
Isn't it no because there's no friction? So isn't it the friction that's stopping the object from moving?
Usually, yes. If it's one object by itself, it's about. So with work kinetic energy theorem, look, that stops because of friction, right? Because it's one object. But I can slide this one and it could stop because it hit the other one, right? So what do we think about here? Can they both stop? Can one stop? What's the whole idea? Can both stop? Can one stop? Because that's the key. They're asking you both questions here, right? Rick, Ed, what do you think?
I said no because one would
No to
still-
what? The first question or the second?
The first one.
Okay.
I said no because one would still have momentum because it's still, like it didn't lose all its energy. And it's,
Careful, don't misconstrue those words. Momentum, not energy. It could lose its energy. So what Rick said is right, though. If this one has momentum, upon collision, one of them has to still have momentum, because the momentum cannot be lost, right? Momentum itself. But then, yes, the actual energy, the friction will cause it to slow down. But the system itself, like give this one 5, that one will have 5, right? Again, it's right after the collision and right before the collision. Yeah, a couple of seconds down the road, there's no momentum, clearly, right? It's going to stop. So the idea is that conservation of momentum is true right before to right after collision or interaction that occurs. It's not true for all time, because obviously they're going to stop, right? Conservation of momentum has to do with the interaction between two things, right before and right after. So one of them has to be moving for sure. But can one be at rest? Yes. And again, you can see that with the erasers. Slide this, it's that one, and this one kind of comes to rest right after it, kind of. If you do it with a billiard table or pool, you'll see it better. The ball will hit and it will actually stop. And all the other one takes on the momentum.
But they're moving towards each other.
They're moving towards each other. If they're exactly equal and opposite, what do you think will happen? If not, they have to rebound. Okay? If there's any imbalance whatsoever in the momentum between two objects moving toward each other, they have to rebound off each other. But if they happen to have the exact same momentum, they can hit and stop. And the concept there would be that the momentum would be transferred or canceled out. But if they stopped upon a collision like that, and they stop, meaning they stay together, it would actually be an inelastic collision if they stop after that collision. They can technically have the same momentum and bounce back also on an elastic collision, which is kind of ridiculous to think about. But you have both scenarios really. But if the momentum, if they're unequal, it has to move after the collision. Only when they're equal, it could stop if it's inelastically colliding. Okay? So that's kind of like 3 scenarios when you think about it. If they're unequal, where this momentum is much bigger than this momentum here, then they will not stop. Because one is much bigger than the other for sure. But the other option is they can still have equal momenta and they can move. If it's elastic, then they will move apart after. Like recoil, they'll both recoil. All these scenarios are possible. Inelastic, they hit and stop, if they're equal. Elastic, they hit and rebound if they're equal. But if they're unequal, they're definitely not going to stop. And they're most likely going to either move together. If it's inelastic, the stick and move this way. Or if it's elastic, this guy will go bam and shoot this one off. And that's the example I gave you with the blob, right? That concept, did I talk about that one with the summer camp? You ever bouncy castle? Did I not talk about this in this class? The other class. It's so hard when you're class to class. You ever been on a bouncy castle before? When you were a kid? Or when you go to block parties and stuff? If you've ever jumped hard enough on a trampoline or bouncy castle as someone else is landing, it usually launches them. You know what I mean? So if you YouTube this, we can look at maybe one thing. If you YouTube The Blob, it's from an old movie I watched when I was a kid, and what they would do in summer camp, they would have this giant lifeguard stand jump into the water, but on the water was a giant, what you would call bouncy castle, I guess nowadays. It was called the Blob. It was this rubber thing that was elastic. One person would jump off the top, and since they were from the top, they had a lot of potential energy. They'd hit, and there'd be a small, you put an adult on top, and then a 3-year-old on the other end. So when the adult hits the bouncy castle, the kid gets launched 4 times as high as the lifeguard stand. It's really actually kind of cool. And it's conservation of momentum and energy, really. Some energy is lost for sure, but it's really conservation of momentum, and it's a transfer of hydraulic pressure, really. It's crazy because you're going to see forces are related to this, really, and pressure is also in here. There's conservation of pressure and force, but that's another ballgame for now. What else? Other questions you want to ask? Let me see if there's anything else I want to add. Anything else you guys want to ask that I'm forgetting? And we've gone over everything that could have possibly asked you on the test. Understand your relationships. Like last test, I gave you a question that said, if you recall, when the velocity triples, what happens to the kinetic energy? And the answer was it went up by a factor of 9. Remember, because velocity was squared. So I'll give you a hypothetical. I'd like to give you something like this in the test. If the mass goes up by a factor of 5, then the velocity is cut in 3. What happens to the momentum of the object? So here's normal momentum. Now give me the new scenario. If the mass goes up by a factor of 5, what do I write then? 5m. And the velocity is cut in 3, what do I write then? 1/3 v. Well done. And I say, what's the overall effect? Well, just look at your variable. You look at your constants. Put the mv on the side, because we know multiplication is commutative. I can multiply in any order. 5 times 1/3 is 5/3, or 1.66 repeating. So, did this person or object gain or lose momentum as a result? Gain or lose momentum as a result? Look at the number. What's the coefficient you start with? That's a 1, isn't it?
Yeah.
And it goes up to 1.6. So you can always do it this way if you'd like. You could also just look at the fraction. It's 5/3, right? And 5 is greater than 3, so it's a larger numerator, so it's going to gain momentum. That's what happens as a result of quintupling the mass and cutting the velocity in 3. There was an example in your homework, I think we were promised it, that, and this is not exactly like the test, but I want you to understand this concept. I could ask it in other ways. There's an example in your homework of the promise that said, if you're an astronaut and you're stuck from the space shuttle, like say you're trying to repair something on the space shuttle in space, no gravitational pull, you're trying to repair something on the space shuttle, and your cord that connects you to the space shuttle suddenly becomes detached. You start floating away from the space shuttle into space, into emptiness. What should you do to get, kind of scared, right? She's kind of look on her face. What should you do to get back to the space shuttle? It happens in gravity. This is part of the scene, actually. But it was a question in your textbook, or your old textbook.
Can't you give the wrench momentum, like by throwing it or something and holding on to it, and there's nothing to stop the momentum that you give it because in space there's no gravity?
Okay, so if I hold on to the wrench and try to push off it, I can't because it's not fixed, right?
Yeah, but
if the wrench were fixed, I can push off it.
Yeah, I mean like not.
I can't hold on to it.
I don't know how to say it. Here, let me look how I wrote it. I wrote it very
Just guessing. Could
Yeah.
you hold on to it, throw it, and then when you release it, you would be back as well?
Think about the skater example at the center of the ice. When you and your friend push off each other, don't you both move? Because the idea is that energy is not lost there. In space, if there's no gravitational pull, if you throw something this way, well, conservation of momentum will cause you to actually recoil back. Just like when you fire a bullet out of a gun, the gun has recoil. Your body is what's holding it in place. But if it didn't, the gun would get launched back. And people have broken shoulders that have tried to use like a shotgun if they've never used it before. You can literally break your arm. So the conservation idea there is what's allowing you to throw it and say it'll bounce you back.
What if you get this and push your legs
Against what?
on space?
Well, the thing is, whatever's in space is not fixed. Like, you push off the wall, if I sit in this wheelie chair and push off the wall, I'm going to get launched this way, right? But the wall, is it going to move? The wall's not moving, really. Yes, I'm applying force, and we would think conservation of momentum, but I'm applying a force. This is really impulse momentum theory. Because this object is not a movable second object. If both objects can move, then you apply conservation of momentum.
But what if you it's just you, put your legs up and you push your legs?
What are you pushing?
air.
You follow what I'm saying?
Yeah.
There's no
But would you
space
move?
is a vacuum.
You wouldn't move,
There's nothing to
right?
push. You could kick all you want. You could try to swim in space. You won't.
But
There's
the
no
force
friction.
you apply to your legs.
Where's it gonna go? Where's it gonna go? You need another object there that's fixed to have an equal and opposite push back, right? There's no second object. You need a second object. Conservation of momentum is only true for two objects. If I have momentum and then I don't, it means that impulse acted. There's no second object, really. It's impulse stopping. But if I have momentum and I hit another object that's free to move, I can transfer said momentum to the other object. But I can't just stop. You know what I'm saying? It's a second object that can move.
But then you move your legs, like if you push your legs with your hands, doesn't that push you back?
Are your legs fixed?
Yeah.
They're not. In space? If you're floating in space, they're not fixed to anything. You follow? Like if you push your legs, which way do they want to move? Forward. And which way do your hands want to move? Back. So what would you be in a state of?
I would move, right?
Yeah, you'd be in equilibrium still. So pushing your own body won't help you, is what I'm saying. You need something else. So honestly, if you're in space, you're better off trying to like hold your breath, take off your helmet, hold your breath in space, throw it, get back to the space station in time, and then take a deep breath. Like you have a better chance, you know what I mean?
Once you freeze.
I mean, this is not realistic, obviously, a lot of this.
What if you do that thing that they do in the movies where they cut the oxygen wire so they like push themselves?
Yeah, that's another one. If there's pressure in a container and you cut the line, you just hold it, it'll just release the pressure, which applies a force that way. Reaction goes that way. It's more like a lot of what ifs. What? You could move yourself and you could try to rotate your body and like this and do this and stuff, and that's fine. But you're not going to make any linear motion. You're not going to cover any ground. It's not ground because you're in space.
So your head would blow.
Those cartoons really like super space.
So inside of a spaceship, obviously, it's totally different. You get, right? In the spaceship, there's air. It's actually pressurized and there's oxygen flowing in. And that's why you see astronauts swimming inside. There's an awesome Apollo 13 scene. Have you ever seen Apollo 13? No? Yes? I say yes. You know the scene when like they get a bucket of stuff and he's like, all right, we need to make this out of this, and all they have is this up there. What happens is their oxygen is the problem. They split their oxygen tank or something happens where they need oxygen or else they're going to die. And they only have a certain amount of parts up in space, so they bring together all these engineers in a room and they say, you need to make this, and this is the parts they have, and you need to somehow make this work. And they have all these crazy like duct tape. It reminded me of like your experiment, your project. But literally, it's like a 1 minute scene. Do I have time? What time does the bell ring on an exam then?
1 minute. Yeah, 1 minute.
All right, let's watch this one because we're done with reviewing. I think for now.
1 minute. I got 3 beats.
I put up a new link on. I put up a lot of links on Newsflow if you guys don't notice. But it's a cool one about Star Wars. Can we shut the door real quick, Andy? I'm not tomorrow, but I'm going to see it for sure. Star Wars.
Oh, that's good.
All right, take a look.
Hey Google, how do you
come
say
on.
I've got a boyfriend in Italian? Oh my God.
So they lose oxygen, Tom Hanks, and a couple others. I want to get to the cool scene now. They're losing oxygen. All right, here we go. That's a famous line. Houston, we have a problem?
Houston, we have a problem.
It's a great movie. You want to see it?
We have a situation brewing with carbon dioxide.
We have a CO2 filter problem within the lodge.
5 filters on the land.
I'm going to skip ahead so you can see where he says it. Come on. It's right here. So that's what they have in space. They need to make this air filter and stuff. And all the engineers come together to build it. All right. Hey, come by after school, please. If you have time, you want to work on your project. They're due tomorrow. I don't see you guys tomorrow, so I need that project in the morning. Drop it off, please. The only thing you're working on during the school day tomorrow, drop it off in the morning.
Oh, Mr. Al, they repealed it. We can drop.
What?
They repealed it. Two already voted to repeal it, and then Clyde didn't even vote it.
You watching live?
It's over. It's over.
Is the laptop outside? Come on, give me that. Yeah. I know it's not yours. Thanks, Sophie. So you're not sure you said you might have a name for practice? Give him a hard time, man. Yeah.
So is the science in Star Trek like actually accurate?
None of that stuff is. So they talk about like even Star Wars and the Force and stuff. Take a look at the news forum, right? The latest video I put up on the news forum is could Jedi really exist in physical way like Jedi's? So they go into like how it's possible, how they have energy necessary to credit.
Yeah,
It's
because
an energy concern,
I was
really.
always curious because I really love those. I also
Right?
they actually
I know, I'm the same boat as you. I was a huge fan.
Yeah.
But no, they definitely don't. Regina, let's find a classroom. There's a class in here right now. So we're going to find a classroom, maybe check 401 or 402, see if they're open this period.
It doesn't seem like we have all this to make this spin to this.
Yeah, it's exactly the scene, right? It's a good one. We got this, and this, and we need to make this. And they come out with this right here. It's like a reducer, which is really what they have to make right here. It's a CO2 filter that takes CO2 and converts it into oxygen.
Italian is over.
Oh yeah.